Thank you for joining this talk on running Unikernels at scale and how we are serving 1 million databases from a single server. My name is Søren Bramer Schmidt, and I'm the co-founder of Prisma. And if you are doing JavaScript or TypeScript on the back end, you might be familiar with us. We are an ORM, and we launched 6 years ago now, just as TypeScript was becoming a thing. At the time, we were looking at TypeScript and Flow, and everybody was trying to figure out what is going to win. And we realized TypeScript is going to win. So we rode that wave, and we're now the biggest ORM in the TypeScript ecosystem. And when you use Prisma, it looks something like this. On the left side, you have the Prisma schema file that you use to define the shape of your data. The data lives in your database. It could be Postgres, MySQL, SQL Server. And then you get a type-safe API to interact with your data. That was kind of the innovation we brought, and we were one of the first libraries to really push the power of TypeScript with conditional typing. And now, of course, everybody's doing that, and we have this huge, amazing ecosystem. And this is our audience. We have about 1 million developers who are using the Prisma ORM. They are disproportionately small companies, relatively low scale, lots of hobbyists. They value a great experience, and they're often working on multiple things at the same time. And then this last one, it surprises me every time I look at the data. 70% of all Prisma users, they use Postgres. So we support SQLite, MySQL, Postgres, MongoDB. But everybody in our little world, they use Postgres. So 2 years ago, we started thinking about how can we build a commercial product that would be a good fit for our audience. It was pretty clear. We should build hosted Postgres. So we started thinking about, well, hosted Postgres. There are lots of options out there. Everybody can go to AWS. You can spin up hosted Postgres. There are more developer-focused competitors. There's something like Supabase, Neon, even Planetscale. So what can we do that is different? And we really wanted to focus on this developer experience. We wanted to figure out how can we make a database that feels more like using something like Notion. Creating a database, can we make that like creating another Word document? That's what we wanted to try to do. And then we wanted a fundamentally different cost structure. When you live inside AWS, every time you create a thing, you're going to have to pay for that thing again and again and again, every month. No matter how much you use it, you're paying for that thing. So that means you try to create fewer things. And we want to flip that around. We wanted you to create lots of databases and only pay for them when you use them. And then we wanted to maintain the high bar on developer experience that Prisma is known for. And of course, we need to get all the basics right with reliability, backups, and compatibility with the existing Postgres ecosystem. So that all boiled down to this one kind of technical challenge. Can we run 1 million databases on a single server? And if we could solve that problem, all of the other things would follow. So before I dive into that, I want to go on this little side tangent. Many of you are old enough to remember when AWS became a thing, and it was a massive shift for our industry. We went from having to physically buy servers and drive them to a colo center and wake up in the night when they didn't work anymore, to this new magical world where you can just spin up a server, it can scale, you have this incredible flexibility. And at the time, it was a pretty good trade. You paid more for those servers, but you got lots of flexibility. And in the early days of AWS, every year, 2 years, you would get good price drops, and it was kind of exciting. You get new models that cost the same, but are much faster. In the last 10 years, that hasn't really happened as much. So if you go and look at the data, you can see that AWS has gotten 40–50% cheaper in 10 years for a given compute resource. But bare metal servers, you just go down to your local hardware store and buy a server. That server for the same money is 10 times more powerful. So if you did a cost calculation 5 years ago, 10 years ago, and decided AWS is the best bet, we have to go and recalculate that now because the world has changed. So that was the first decision we made. We're going to build this thing outside of AWS. We rent a rack space with Equinix, and we put in relatively modest servers like this one. So big picture, the traditional approach to building managed Postgres is what all of our competitors are doing. They operate a small VM or a small instance per tenant. And if you go and rent them from AWS, well, the smallest one you can get costs $3. So that means if you're trying to operate 1 million databases, that costs you $3 million a month. That's a lot of money. So you don't want to have too many of those databases. You certainly don't want to give them away for free. We've seen some of our competitors do exactly that, have a free tier, then realize, we're spending millions of dollars on a free tier. We have to stop this free tier. It's madness. So our approach, can we fit 1 million databases on a single $750 per month instance? And then we can operate 1 million database for $750. That would be great. So how do you fit 1 million databases on a single server? And this is what ChatGPT thinks it looks like. Just cram them in there. But let's boil it down to some technical constraints, technical requirements. On this server, our memory is constrained to 256 gigabytes, so we cannot keep all the databases active all the time. That just wouldn't fit. We also want to ensure we don't introduce any noticeable cold start latency. We don't want requests to ever take more than 10 milliseconds. And then it must behave as a regular Postgres database. We cannot ask our users to do special requests to start and stop the database or something like that. It has to feel like a normal Postgres database. So for the first constraint, constrained memory, there's this simple idea. What if databases don't serve requests all the time? And what if we could just pause them and take them out of memory and then resume them again later? That's how stateless services work. That's how Lambda works, and it works really well. But could you do that for stateful services? And it turns out you can, if you are a little careful and put some constraints in place. So it looks something like this. This is the lifetime of a database. And when it has been idle for a while, it receives a request. Then we start it up really fast. We load it into memory. And then we keep it running for a while in the hope that another request comes in. And if that's not the case, we'll pause it again, take it out of memory. And then another request comes in, we bring it back up. We run it until it stops receiving requests, we pause it again. That's the general idea. We are running these databases in Firecracker. Firecracker is the micro VM technology that is powering AWS Lambda. And traditionally, that was really only meant to work with stateless services. But a few years ago, they introduced support for memory snapshotting. And memory snapshotting is a very basic idea. You have your running VM, you pause it, and then you take all of the bytes in memory, you just write them to disk. Then when you want to restore it again, you take all of that bytes, you write them into memory, and you resume your VM as if nothing had happened. AWS is using this in limited ways for AWS Lambda Snap Start for Java, because Java applications are really slow to start. So they developed this technology to make the startup overhead of Java applications go away. Snapshot and restore is a pretty heavy process. That's why we keep them around for 5 seconds, even if they don't serve requests. We hope that a request will come in and it's worthwhile to keep it around. So some basic math means that with 250 concurrent databases, about 1 gigabyte each, then we can serve 180,000 different databases in an hour. And it turns out for our particular workload, we have a very long tail. So we have some active databases and we have some databases that just do nothing for days. This approach actually works really well for us. But it brings us to the next constraint, the no cold start constraint. We want to make sure that a request can be served in single-digit milliseconds, no matter what. And we know because of the long tail of our workload, we'll have lots of databases where the requests they receive will be a majority cold starts. So the cold starts need to be really, really fast. And it turns out this problem is mostly around disk speed. It has nothing to do with the performance of your CPU, the amount of memory. It is all about how fast can you read and write to your local disks. So we don't use network attack storage or anything like that. We get the fastest NVMe disks we can, physically attach them on the server. And for not that much money, you can get really fast NVMe drives that can read 15 gigabytes per second sequential reads. So that means in 10 milliseconds, we can read 150 megabytes. But that's a problem, because each of our databases, they run in a 1 gigabyte micro VM. So how do we overcome that? Well, there's a trick we can play. Most of that data in the micro VM is really just data that Postgres has cached. It's not data that we really need, it's just there for convenience. And most likely the first query coming in, it doesn't need most of that cached data. So what we do is we load up, when we restore a VM, we load up only the data we need to run Postgres itself and kind of get going. And then we let Firecracker kind of page in the remaining data as needed. So maybe the first request doesn't need any of that, but then you get a heavy request that does a table scan, and a lot of Postgres thinks a lot of that data is in its page cache, but actually it has to go out and page that in from disk, and that's okay. And now we come to the Unikernel part, because loading just Postgres and just the operating system is fine, but there's still a meaningful amount of data. And it's actually more than 150 megabytes if you're not careful, because you need the full operating system, you need the full Postgres and everything to get that running. And to solve that problem, we worked with a team called Unicraft that has been working on this Unikernel technology for about a decade now. How many of you are familiar with the idea behind Unikernels? A few down here. I spoke to you earlier. These guys work with Unicraft in an academic setting, so if you have more detailed questions, find them afterwards. When I studied computer science 15 years ago, I knew of this idea of Unikernels, but I also knew that it was nowhere near production ready. And it turns out in the last few years, it has kind of crossed that point. You can now use Unikernels as a thing you can actually operate in production. This is a graph from the Unicraft team. On the left side, it shows the traditional kind of architecture stack. On the bottom, of course, you have your hardware, you have your virtualization layer, then you have the monolithic kernel, it would be the Linux kernel, you have the bits and pieces of the operating system, and then you have the third-party libraries you depend on and your application. All of that needs to be packaged up into a single VM and run on your hardware. What Unicraft does, it takes all of that as input to a compile step that then generates what they call a Unikernel binary image. And the Unikernel binary image, it contains a heavily modified version of an operating system that can only run one program, your program. So all the things you don't need for your program, it's not there. Also, all the checks that you need to have in the Linux kernel in order to support multiple programs without having them step on each other and crash, all of those checks are gone. So traditional I/O operations are faster, and your resulting image is meaningfully smaller. So we make use of that, and it enables us to start up our database VMs meaningfully faster because the resulting image is about half the size. And as a result of that, we can resume databases in less than 10 milliseconds. And then the last constraint. We want this system to behave as regular Postgres. Under the hood, it's a heavily modified Postgres running in a weird operating system inside a Firecracker micro VM. That is probably asleep when you want to connect to it. And we want our users to know nothing about any of that. A client should not be able to tell whether a database is suspended or active when connecting. All it should see is a slight variation in latency. So we handle this by implementing a stateful proxy. We've written it in Go, but you could do whatever is your language of choice. It sits on each host, and it accepts incoming connections. So when you have your Postgres client or a database UI tool, you connect to your database. What you're actually connecting to is our Go proxy. It accepts the connection and just holds on to it for a little bit. Then at the same time, it goes out to the micro VM subsystem and figures out that database is that running. If not, let's get it back into memory. Then it hands off the connection to the micro VM, and then your client can continue the Postgres protocol. It also handles OAuth and global routing and a bunch of other stuff. And I think I need to start using ChatGPT for my architecture diagrams because I kind of like what it's doing. So this is the full picture. We operate data centers in rack space rented from Equinix in 5 regions. That was a new thing for us. We had never done that, but it turned out to be pretty pain-free. You can just talk to them and get this going in a few months. It's not that expensive. In each region, we operate multiple servers, and each server is able to accept incoming connections from any customer. A new connection lands at the proxy we just discussed, and then routing is performed based on a distributed store containing information for all of the databases that we're operating. The connection might terminate on the same server if your database happens to be on that server, or it might be proxied to another server in the same region, or if for whatever reason you're connecting to a database that is far away from you, well, then we're going to proxy you to that region, directly to the instance where your database is on, and then we terminate your connection with a Postgres VM that we might have to spin up. Maybe it's already active. So this was a bunch of interesting technical stuff. And if you want to dive into more of the technical details, I'm very happy to. We have some technical blog posts you can read. I'll be in the speaker's corner afterwards, and I would love to dive into any of that. But for us as a business, what does it mean? It means that we are able to offer a generous and sustainable free tier. You can sign up to Prisma Postgres, and you can have up to 50 databases for free. You can do 1 million requests to that database every month for free. And it costs us basically nothing. That means we can continue to operate this free tier forever. As an end user, you don't have to be worried about it going away. And we don't have to worry about having to scale up a business to support it fast enough. We're also able to create databases in about a second, which is really fast. And it gives us the freedom to experiment with different marketing things. For example, we have made this create-db CLI command. So any of you can run this in your terminal right now, npx create-db, and it'll just create a database for you. No need to sign in or anything. You just run this thing. In a second, you get a Postgres connection string. That's super cool for tutorials, and we encourage everybody to just use it. And it also gives us a competitive product that can power modern platforms. You're probably aware, but AI is a thing, and we have seen that some of these platforms have started in the last year, really, that deploys massive amounts of applications. Bold and Lovable are the big ones, Replit. They each deploy applications, databases in the millions per week. And if you're trying to just deploy that to regular AWS infrastructure, it gets really, really expensive. So we are working with some of those. Alchemy is a modern take on Terraform. It's a TypeScript version of Terraform, and if you're into kind of infrastructure as code, you should check it out because it's really neat. And last month they integrated Prisma Postgres, and they came back to us and said, "Hey, we think something is broken." And this is just because it was so fast. They had never seen that before. They thought surely their test must be wrong. We also integrated with Dino. So if you go to Dino Deploy and use their cloud product to spin up a new project, well, we are the database of choice for them. That's it. Thank you for coming, and I would love to connect with you if you are interested in any of the technology. If you want to talk about the benefits you can get from operating your own hardware and really have this high density setup. So just come and find me afterwards or reach out to me online.